Hello. In the last class, we understood how a given signal can be decomposed into its odd portion and even portion. And we also understood that uh, the odd and even portion added together will give me the original signal. So in this class, let us see one more classification of signals that is periodic and non-periodic signals.
Okay, so let us see the next classification, that is periodic and non-periodic signals. So a signal is said to be periodic if it satisfies the condition x at t plus capital T is equal to x of t for all t here t is a positive constant. Okay, so as all of you know, if the condition is satisfied for t equal to say t naught, that means x of t plus t naught is equal to t. You know that even for t is equal to 2 times t naught, it satisfies. That is x of t plus 2 t naught is equal to t. Sorry, it is equal to x of t. It is equal to x of t, x of t. And similarly, say for example, t is equal to 3 t naught, x of t plus 3 t naught is equal to x of t, so on and so forth. So all the integer multiples of t naught, the condition satisfies. However, the smallest value for which x of t plus t is equal to x of t is called the fundamental period. Is called the fundamental period. So in this case, T naught is the fundamental period. And usually this T naught is expressed in seconds, microseconds, milliseconds. Reciprocal of this T naught is F naught. It is 1 by T naught, and this is called the frequency, which is expressed in hertz or cycles per second. And we define one more frequency called angular frequency. Omega, given by 2 pi f naught, which can also be written as 2 pi by t naught, and the units of this will be radians per second. Okay, so this is how you can define a signal to be periodic. Suppose if x at t plus capital T, if it doesn't satisfy for any period the equation, then such a signal, we call them as non-periodic signals or aperiodic signals. Okay, so let us take a simple example to verify a given signal. Say x of t is a sine omega naught t. So I would like to verify whether this is a periodic signal or not. So the condition to be followed is calculate x at t plus capital T. So on the right hand side, replace t by t plus t. So this is a sine omega naught t plus omega naught capital T. And all of us know that this will be equal to a sine omega naught t if omega naught into capital T is integer multiple of 2 pi. Okay, so as you can see, omega naught can be written as 2 pi by t. Therefore, in this equation, you can write a sine omega naught t plus 2 pi by t into t, and t cancels with t, and since it is integer multiple of 2 pi, the condition is satisfied. So x of t plus t is equal to x of t for sinusoidal signal. Therefore, I can say it is a periodic signal. The given signal is a periodic signal. Let us verify this condition for discrete time signals. Discrete time signals. So the definition is, for signal to be periodic, x of n plus capital N should be equal to x of n for all n, and here n is a positive integer. Only if n is a positive integer, then the condition is true. So again, the smallest value of n which satisfying the above equation is called fundamental period. Fundamental period. So here again we define a frequency called angular frequency, which is designated as omega. The symbol is ohm, as you could see. So it is 2 pi by capital N. So the limits is so many radians per sample. Radians per sample. Okay, so this is how I can verify whether a given discrete signal is periodic or not. If the condition is not satisfied, that means x of n plus capital N is not equal to x of n, then such signals are called aperiodic or non-periodic signals. Okay, so we will take one example to illustrate this in discrete domain also. For example, Okay, before taking the example, there is one observation that all of us should know here. T, which is the time period specified for continuous time, can be any positive value. It can be any positive value. That means I can have it as 1 second, I can have it as 1.01 second, I can have it as 1.001 second. So it can take any positive value. However, n has to be a positive integer. So this is the difference between discrete and continuous period. Capital N has to be a positive integer. So let us take an example now. Say given that x of n is minus 1 to the power of n. So we need to check whether this is periodic or not. So the condition to be followed is x of n plus capital N should be equal to minus 1 to the power of n plus capital N. Replace n by n plus n. This can be written as minus 1 to the power of n into minus 1 to the power of capital N. And as you can see, this value is equal to minus 1 to the power of n for even values of n. Okay, so even values of n means it can be 0, 2, 4, 6, etc. So the smallest non-zero value is 2. Therefore, I can say x of n is minus 1 to the power of n is periodic with period n is equal to 2. So this is a periodic signal. So we should take one more example. Say x of n is cos of 2n. So let us substitute the condition x of n plus capital N is cos of 2n plus capital N. This is equal to cos 2n plus 2n. So you can observe here for no value of this, for example, for this to be equal to cos 2n, 2 capital N should be integer multiple of 2 pi, and which means that n should be equal to n into pi. And as all of you know, capital N has to be an integer, and for no value of this small n, this number will be an integer. Okay, so therefore this condition is not satisfied. That means for no value of n, x of n plus n will be equal to x of n. Therefore, this is an example for non-periodic signal. This is an example for non-periodic signal. Okay. So even though it looks like a cos signal, you can observe that since it is a discrete signal, it is not periodic. So we will just consider one more homework problem. Check whether x of n equal to cos of 2 pi n, whether it is periodic or not. If it is periodic, find the period. So in this class, we understood how signals can be classified into periodic and non-periodic signals. In the next class, we will consider another classification of signals, that is deterministic and random signals. Thank you.